Welcome to the Bodhi Academy. My name is Amsha Klasso, and in today's video we'll continue the class 11 chapter 6 equilibrium. So in today's class we will have the continuation. Previously we spoke about the applications of equilibrium constant. In that the two major applications we discussed was that first it was able to predict the extent of the reaction, and also second one was that it is able to predict the direction of the given reaction. Now talking about the predicting the extent of a reaction. So the numerical value of the equilibrium constant for a reaction indicates the extent of a reaction. But it is important to note that an equilibrium constant does not give any information about the rate at which the equilibrium is reached. So the value which we get, the Kc value which is being found over here, it indicates the extent of the reaction, so as to how long will the reaction proceed, but it is not at any point defining to us that how long or what is the rate at which this equilibrium is being reached, what is the speed or how long it takes for this equilibrium to reach. So the magnitude of Kc or Kp, it is directly proportional to the concentration of the products, because we know the formula is Kc equals to concentration of products upon product of concentration of reactants. So it is directly proportional to the products which are in the numerator, and it is inversely proportional to the reactants concentration. So Kc and Kp is directly proportional to the concentration of products in the numerator of equilibrium constant, and it is inversely proportional to the concentration of the reactants. So now this implies that high value of K is suggestive of a higher concentration of products. Higher the value of K tells us that the concentration of products is more, and vice versa. So if value of K is less, it will tell that the product formation is less. So we can make following generalizations concerning the composition of equilibrium mixtures. So based on this, we are able to make three major assumptions or generalizations based on this above understanding of ours. So first one says that if Kc is less than 10 raised to 3, okay. So here what will happen is that the products which are there, they predominate over the reactants. That is, if Kc is very large, then the reaction proceeds nearly to completion. So if the value of this Kc is very large, then we can say that the reaction is going to be almost to completion. That is, all of the reactants are going to get converted to the products. Now some example of this would be, let's look at the first one, the reaction of H2 with O2, hydrogen gas with oxygen at 500 Kelvin. It has a very large equilibrium constant, that is, it has a equilibrium constant of 2.4 into 10 raised to 47, so which is quite high. So here what we can say that all of the H2 and O2 have reacted to give us the products, correct? Next, let's talk about H2 plus Cl2, which gives us HCl. Here also, if you see, the Kc value, equilibrium constant, is quite high. So we can say that the reaction was almost complete, that is, majority of the reactants have converted to form HCl. Last we have H2 plus Br2. Here also it is significantly enough, yet we can say that the reaction had proceeded to almost completion. So now if Kc is very small, then the reactants which are there, they are the dominating one, they are the ones dominating over the products, okay. In such cases, we can say that the reaction proceeds rarely, as in rarely there will be formation of products that is happening. First example, the decomposition of H2O into H2 and O2 at 500 Kelvin has a very small equilibrium constant. It has an equilibrium constant of minus 48. So here what we can say that decomposition of H2 into H2 and O2. So almost like a lot of H2O is still remaining on the reactant side, which is not getting converted to the product, okay. Same way, N to N O2, here also we have a quite lesser value of equilibrium constant. So we can say that the reaction rarely proceeds. Next is that if Kc is in the range of 10 raised to minus 3 to 10 raised to 3, that is in between values now. So appreciable concentrations of both reactants and products are present. So now what they are saying, if the value of Kc, it ranges between 10 raised to minus 3 and 10 raised to 3, then we can say that there is appreciable concentration, as in there is almost enough concentration that is left over on both the sides, on the reactant sides as well as the formation of product sides. So if we consider this example, say for reaction of H2 with I2 to give HI, then Kc over here will be equal to 57.0 at 700 Kelvin. Also, gas phase decomposition of N2O4 to NO2 is another reaction with a value of Kc which equals to 4.64 into 10 raised to minus 3 at 25 degrees Celsius, which is neither too small nor it is very large. Hence, here we can say that the equilibrium mixtures, they contain appreciable amount of both N2O4 and NO2. Now, if we have to generalize all of these three types, all these three generalizations into illustration, this is the basic understanding of what we have learned. So, if it is less than 10 raised to minus 3, that is almost negligible. 10 raised to 3, it is extremely large. Beyond this, then extremely large. So if here we can say at this end, the negative end, we can say that a reaction hardly proceeds, okay, hardly any reactants are getting converted to the products. If we have extreme other side, the positive side, we can say that almost the reaction is occurring, going towards the completion phase. And if it is in between, that is 10 raised to minus 3 to 10 raised to 3, we can say that there is equal amount of reactants and products that are present at the equilibrium point. Okay, so first we discussed about the predicting the extent of the reaction. Now we discuss the prediction of the direction of the reaction, in which direction is the reaction going to proceed. So the equilibrium constant, it helps in predicting the direction in which a given reaction will proceed at any stage. So equilibrium constant can also tell us about in which direction the given reaction can actually proceed. Now for this purpose, what we do is we calculate the reaction quotient, that is Q, okay. So the reaction quotient Q which is there, QC with molar concentrations and QP, that is with partial concentration, it is defined in the same way as the equilibrium constant Kc, except for over here we do not consider the concentrations at their equilibrium values. We can take any in between values as well and try to define this reaction quotient. For example, if we have say a general reaction of A plus B giving C plus DD. The small a, small b, small c and small d are the stoichiometric values. So QC will be written exactly the same way as we write for Kc. So concentration, product of concentration of products upon product of concentration of reactants. Now over here also we are making some generalizations. We have three generalizations. So first is that if QC is greater than Kc. So what we are saying here is that if the value of QC, that is the quotient, reaction quotient, is greater than that of the equilibrium constant, then we can say that the reaction, it will proceed in the direction of the reactant. So that is reverse or backward reaction, okay. So if QC is greater than Kc, then it will go into the reverse direction, that is it proceeds in the direction of the reactants. So that is more and more the products are going to get reduced into the reactants. Now if Kc is greater than Qc, the exact opposite is going to happen. The reaction will proceed in the forward direction, that is more towards the product. So the reactants are going to react in order to give us more and more concentration of products. Last, if Qc and Kc both are equal, then we can say that the reaction mixture is already at equilibrium, okay. So three major generalizations. First is if Qc is greater than Kc, the reaction goes in backward direction, that is it goes more towards the reactant side. If Kc is greater than Qc, the reaction goes into the forward direction, that is it goes more towards the product side. And if Qc and Kc both of them are equal, we can say that the reaction mixture has already attained equilibrium. Now let's consider the gaseous reaction of H2 with I2. Say we have H2 gas plus I2 gas, okay. This, it reacts to give us hydrogen iodide. Its Kc value is 57 at 700 Kelvin. Now suppose we have a molar concentrations of this, we have given all the reactants as well as the products, the molar concentrations are given. Thus from here the reaction quotient Qc at this stage of the reaction is given by 8.0. So on calculating we get a reaction quotient to be 8.0. Now in this case QC does not equal to Kc. So here Kc is 57 and QC is 8. So which is greater? We have Kc which is greater here, and if Kc is greater, what did we say? That the reaction will proceed into the forward direction. So now in this case it does not equal to Kc. So mixture of H2 and I2 and HI is not at equilibrium. That is, more H2 and I2 will react to from the hydrogen iodide, and their concentrations will decrease till QC becomes equal to Kc. Okay, so they will go on reducing till both of them come at the same level and have the same values. Now the reaction quotient QC, it is useful for predicting the direction of a reaction by comparing the values of QC and Kc. So here we have basically compared the values of Qc and Kc, and based on that we are able to make a general prediction of so as to in which direction the reaction is going to proceed. So thus we make the following generalizations concerning the direction of the reaction. So if you see here, this is the reactants and the products. So Qc is less than that of Kc, then it will go into the forward direction, that is more and more products are going to be formed. So this is the forward direction. If QC is greater than Kc, then it goes in reverse direction. Products are going to get reduced to reactants, and if both are equal, only then we can say that the reactants and products are at equilibrium. So if Kc is greater than Qc, net reaction it goes from left to right. If Qc is greater than Kc, then the reaction goes from right to left, and Qc equals to Kc, there is no net reaction that is occurring. So this is how we can predict the direction and the extent at which the reaction is going to occur. Now next let's look at so as to how to calculate this equilibrium concentrations. Okay, so in case of a problem in which we know the initial concentrations but we do not know any of the equilibrium concentration, the following 3 steps shall be followed. So first one is that write the balanced equation for the reaction. So you write whatever reaction is given, in that you write the balanced equation. The stoichiometry should be balanced throughout. Second, what you do is that you write under the balanced equation itself, you make a table that lists each subjects that are involved in the reaction. Say there are 2 reactants and 1 product, you list down all of them right below the balanced reaction. Now in that table, first you write the initial concentration, so as to what concentration you had initially started the reaction with. Second, you write the change in concentration on going to equilibrium. So whatever change has occurred is what you are going to write in the second column. And third, you write the equilibrium constant. Okay. Now in constructing the table, you have to define X as the concentration, that is mole per liter of one of the substances that reacts on going to equilibrium. Then use the stoichiometry of the reaction to determine the concentrations of the other substances that are given in terms of X itself. Third, what you do is that you substitute the equilibrium concentrations into the equilibrium equation for the reaction and solve for X. Okay, here you can use any mathematical quadratic equation solving methods and find the value of X. Then you calculate the equilibrium concentrations from the calculated value of X and check your results by substituting them into the equilibrium equation. So say one problem, if we look at, we have 13.8 grams of N2O4 which was placed in 1 liter of reaction vessel at 400 Kelvin and allowed to attain equilibrium. So reaction which is undergoing here is that N2O4 is going to 2NO2. Now here the total pressure at equilibrium was found to be 9.15 bar. Now we have to calculate Kc, equilibrium constant, Kp and the partial pressure at the equilibrium. So first what we can do is we can use the ideal gas equation, because we are talking in terms of gases over here. So Pv will be equal to nRT. Here we know volume we can consider to be as 1 liter, which is given in the question itself. The total molecular mass we can find of N2O4, which comes to be 92 grams. Now from this information we can find the number of moles. Okay, so if we have the given mass, that is 13.8 upon the molecular mass, that is 92. So on finding its ratio we get 0.15 as the number of moles that are present. Gas constant we know 0.083 bar liter mole inverse Kelvin inverse. Temperature is going to be 400 Kelvin. On substituting all of this value in the ideal gas equation, we tend to find the pressure to be as 4.98 bar. So 4.98 bar is the initial pressure, whereas the actual pressure is 9.15. So 4.98 minus x, that is we don't know the initial the final pressure, bar 2x. So at P total at equilibrium will be pressure of the both the reactants as well as the products. So 9.15, that is the total pressure, equals to 4 this whole equation we are going to substitute here, and we'll find the value of x, that is at equilibrium what was the concentration. So partial pressures at equilibrium are, you then substitute and you find the values of the partial pressures. So if Kp equals to, you write the equation, so P NO2 the whole square, because it has a stoichiometry of 2, upon P N2O4, on substituting we get 85.87. Then you can find the value of C also. We know there is a relation directly given, Kp equals to Kc RT raised to N. N we know is number of moles, so we can directly substitute and find the value of Kc, which comes to be around 2.6. So that is how we can calculate the equilibrium constants for a given reaction that occurs. So that was it for today's video. I hope you have understood. Please don't forget to like, share and subscribe to the Bodhi Academy.